Okay, good afternoon. Today we will see some experiments of robotics on virtual labs, that is Ministry of Education Government of India initiative. Now this is the virtual lab experiments of IIT Kharagpur. See here, this here mechanisms and robotics lab IIT Kharagpur. Then if you click that, it will open this window. Therefore, introduction. Mechanism and robotics are the two vital and broader area of study and research within mechanical engineering. Mechanisms are used in a variety of fixed motion generation applications in engineering, whereas robots are used in applications where programmable motion is required. This laboratory provides a primary exposure to design and control of such motion control applications in various applications, ranging from 2D planar mechanisms to that of spatial mechanism design. A spatial mechanism design, a set of experiments are offered concerning position, velocity and acceleration synthesis and analysis for basic motions. So within this lab, we will study about some open and closed chain mechanism as well as simulation of some industrial robots. Therefore, this is the introduction of this lab. Now list of experiments. Now first 3 experiments and last experiment is of robotics. Therefore, we will see one by one. Now this first experiment is forward kinematics of MoveMaster RM501. First is introduction. Mitsubishi MoveMaster RM501 is a entry-level industrial robot with 5 rotational joints having 5 degrees of freedoms. Forward kinematics refers to the use of the kinematic equations of a robot to compute the position of the end effector from specified values for the joint parameters. The kinematics equations of the robot are used in robotics, computer games, and animation. The reverse process that computes the joint parameters that achieve a specified position of the end effector is known as inverse kinematics. The essential concept of forward kinematic animation is that the position of particular parts of the model at a specified time are calculated for the position and orientation of the object, together with any information on the joints of an articulated model. So, for example, if the object to be animated is an arm with the shoulder remaining at a fixed location, the location of the tip of the thumb would be calculated from the angles of the shoulder, elbow, wrist, thumb, and knuckle joints. 3 of these joints, the shoulder, wrist, and the base of the thumb, have more than 1 degree of freedom, all of which must be taken into account. If the model were an entire human figure, then the location of the shoulder would also have to be calculated from other properties of the model. Therefore, this is introduction of this MoveMaster RM501. This is the diagram. This is the robot manufactured by Mitsubishi. Now we will see theory. Theory MoveMaster RM501. See here. The Mitsubishi MoveMaster RM501 is a robotic arm having 5 degrees of freedom with 5 rotational joints. The robot unit consists of waist, shoulder, elbow, wrist pitch, and wrist roll. These are actuated with DC motors to each of which two encoders are associated, which allow differential directional information to be read for each joint. Overall size. The robot unit, including the base, weighs approximately 27 kg. The overall size of the robot is comparably small, with a circular work envelope of 445 mm, maximum horizontal reach, and a maximum payload of 1.2 kg. Therefore, this robot can lift the weight up to 1.2 kg. Components. In addition to the robot itself, the complete robotic system for the Mitsubishi Move Master consists of several components, which are shown in the following figure to see that different components of the robot. We will see here, for this is the robot. Now robot consists of this end effector, this is the, or which is known as gripper, this is the arm of the robot, this is the base of the robot. Now this robot is connected to the drive unit. Means already you are knowing that mostly robots are electrically driven. There are three types of drive units: hydraulic, pneumatic, and electrically driven. Therefore, this robot is electrically driven robot. This is the kinematic controller, and the same motion is given to the computer. The main components of the RM501 include the robot and the drive units. Options include the teaching box and the standard hand. The RM501 drive unit provides the intelligence and control for the robot unit. The drive unit computes all arm control information for each instruction. It handles arm velocity, acceleration, deceleration, and movement trajectories for the user. The teaching box allows a user to manually move all joints of the robot unit and store positions are desired. The drive unit is interfaced to the computer host processor via a controller interface. Range of movement of each joint: waist joint 300, shoulder joint 130, elbow joint 90. I think it is in degrees: 300 degree, 130 degree, 90 degree. Wrist bend plus minus 90 degree, wrist roll plus minus 180 degree. Now robot kinematics. Kinematics, you are knowing, kinematics means study of motion. Therefore, robot kinematics involves computing the end effector position from the joint angles and vice versa for controlling the position of robot. The Mitsubishi RM501 robot has 5 degrees of freedom, figure 2, and the ability to grip with its two fingers. See that this robot has 5 degrees of freedom. How it is 5 degrees of freedom? This is 1 at the base, this is second, this is the third, this is fourth, and this is fifth. The Mitsubishi RM501 robot has 5 degrees of freedom, figure 2, and the ability to grip with its two fingers. Its position can be described by the vector of joint coordinates Q is equal to Q1, Q2, Q3, Q4, Q5 transpose, and the vector of external coordinates R is equal to matrix of X, Y, Z, Phi, Psi transpose. Figure 3 shows the robot's arm with its basic dimensions from which the kinematics can be derived, that is, the link between the Q and R vectors. Now we'll see this forward kinematics. Forward kinematics. Forward kinematics involves computing the position and orientation of the end effector when the relative movements at various connections and other relevant geometrical parameters are prescribed. The forward kinematics of a kinematic chain can be established by defining a coordinate system at the root of each link and then defining transformation matrices between subsequent coordinate systems as A1 0 A21 A32 dot n minus 1. For rotational joints, each matrix will then contain the joint angle I cap n as a variable. The overall transformation from the earth fixed reference frame to the end effector fixed reference frame is then given by an 0 is equal to a1 0 into a2 1 into a3 2 an minus 1. For each joint of the robot ai minus 1 I, the Denwitt-Hartenberg matrix contains four parameters that fully define coordinate transformations from the coordinate system attached to the previous link to the coordinate system attached to the next link. The four parameters and the description of their meaning is given in table. Parameter description ai, the distance between zi minus 1 and zi measured along xi. Alpha I, the angle between zi minus 1 and zi measured along xi. Di, the distance from xi minus 1 to xi along zi. Theta I, the angle between xi minus 1 and xi measured along zi. Therefore, this is the modified Denwitt-Hartenberg notation. See here, this is the standard form, this is the modified form. This is joint I minus 1, this is joint I, this is joint I plus 1, this is the link I minus 1, this is the link I. The Denwitt-Hartenberg parameters derived for the Mitsubishi MoveMaster RM501 is given in table below. The schematic of the robot with the intermediate coordinate systems used to derive the matrix is given in figure. Now table, it consists of different columns I, AI, alpha I, di, theta I, home. Now for I is equal to 1, AI is equal to 0, alpha I minus 90 degree, di 250, theta I, theta west, and home it is 0 degree. Similarly, for different values of I, that is 2, 3, 4, 5, these are the values of AI, alpha I, di, theta I, and home. I will read this. For 2, 220, 0 degree, 0, theta shoulder minus 90 degree. 3, 160, 0 degree, 0, theta elbow 90 degree. 4, 0 minus 90 degree, 0, theta wrist pitch 0 degree. 5, 0, 0 degree, 215, theta wrist roll minus 90 degree. Now robot, this is the figure, robot schematic showing link coordinate systems used for deriving Denwitt-Hartenberg matrix showing soft home position. Now from Schilling is the book of the robot 1990. The R matrix can be derived by analogy to the general R matrix for 5-axis articulated robot. Now this T base tool is equal to this is the matrix I will read C1 C234 C5 plus S1 S5 minus of C1 C234 S5 plus S1 C5 minus C1 S234 C1 into bracket A2 C2 plus A3 C23 minus D5 S234 S1 C234 C5 minus C1 S5 minus S1 C34 C234 S5 minus C1 C5 minus S1 minus S34 S234 S1 into bracket A2 C2 plus A3 C23 minus D5 S234 minus S234 C5 S234 S5 minus C234 D1 minus A2 S2 minus A3 S23 minus D5 C234 0 0 0 1. This matrix can be understood as being composed of a vector P defining the position of the end effector in space and a 3 by 3 matrix R defining the orientation of the end effector. Therefore, T base 2 is equal to R11, R12, R13, P1, R21, R22, R23, P2, R31, R32, R33, P3, 0001. Therefore, this is nothing but the theory of the forward kinematics of Move Master RM501. Now we'll see objective. Objectives are first to identify the geometric relationship between input and output motion parameters of Move Master RM501 robotic arm, formation of the transformation matrix through which a relationship is established between different links of the manipulator, to have a brief idea about the workspace through a 3D graph plot of manipulator position for various inputs, simulate the robot motion for various inputs of the joint angular value, robot trajectory visualization while moving from one position to another. Next is procedure. Now procedure, insert different values of theta within the joint range as prescribed in theory part, and then click OK to get the output orientation and position of the end effector. To see the second objective, to see the individual movements of the robot links, drag the sliders on the controller panel. Manipulator position is shown in a 3D graph for every submission of joint values. The view can be rotated about a point by keeping the left mouse button pressed and rotating the mouse. The view can be translated by keeping the right mouse button pressed and translating the mouse in the desired direction. The scroll button or middle mouse button can be used for zooming. Therefore, this is the procedure. Now we'll see the simulation. According to this procedure, we will enter the values of different angles. Okay, we will go by procedure. Insert different values of theta within the joint angle range as prescribed in theory part, and then click OK to get the output orientation and position of the end effector. Therefore, different values of theta we will see. First is, these are the different values of theta, alpha I and theta I. Alpha I means the angle between the zi minus 1 and zi measured along xi. Okay, these are the values. Alpha I is nothing but plus minus 90 degree, and theta I is equal to again plus minus 90 degree, theta 1, theta 2. Now we will put some angles here. Theta 1, suppose we will put 40. Theta 4 we will put suppose 50. And theta 5 we will put suppose 60. Okay. Range for theta 3 should be within 0 to minus 180. Yes, it is correct. Range of theta 3, 45 I will put. 0 suppose I will put. Now see that it is processing. See that how it is moving. Then to see the individual movements of the robot, links drag the sliders on the controller panel. Now these sliders are there. We'll drag it. See that how these are moving. Then manipulator position is shown in a 3D graph for every submission of joint values. The view can be rotated about a point by keeping the left mouse button pressed and rotating the mouse. Okay. Now we'll see workspace. Okay, please wait. See that how this, if you will enter the angles, how the position has been changed. Now we'll see the workspace. Here workspace is there. Okay, workspace is generated. We'll wait. Okay, workspace is generated. Okay, now we'll see next experiment. Simulation now quiz we'll see. Now we'll solve quiz. What is the number of degrees of freedom in Move Master RM50? I think it is 5. Next. Next. Okay. How many joints are there in the wrist of the Move Master RM501 robot? One joint. What is the PX positional value of the Move Master robot in a configuration 60 minus 45 minus 40 We'll see this. What is the maximum payload of the robot? 1.2 kg. What is the range of wrist roll plus minus 90? See that I have got 2 marks. First is correct. How many joints are there? 2 joints are there. I have taken 1. What is the PX position value? I have taken A option. Correct option. I have taken C option. Correct option is A. Maximum payload 1.2 kg is correct. What is the range of the wrist roll? It is plus minus 180. And these are the references. These are the NPTEL lectures. Now we will see next experiment. Forward kinematics of Puma 560. Puma is the name of the company which manufactures the robot. Now see that I will read this introduction. Forward kinematics of Puma 560. Introduction. The Puma 560 is an industrial robot arm with 6 degrees of freedom and all rotational joints. In this experiment, at first, a brief theory about Puma 560 robot is presented in the theory section. The theory for mathematical computations was obtained from a wide variety of sources encompassing books, papers, and internet. In simulation section, a virtual model is developed in JavaScript program which is used to investigate the forward kinematics problem. For more information on other aspects of Puma 560 and robotics, visitors are advised to follow the references. Now this is the Puma 560 robot. This is the base. This is the robot arm. This is the end effector. It has one, two, three, four, five joints are there. Now theory, programmable universal machine for assembly, more popularly known as Puma. Programmable universal machine for assembly is an industrial robot arm developed by Victor Shinman at Unimation in the year 1978. Puma comes in various makes with Puma 260, Puma 560, Puma 761, etc. Figure 2 shows link frame assignments in the position corresponding to all joint angles equal to 0. Here the frame 0 not shown is coincident with frame 1 when is 0. Note also that for this robot, as for many industrial robots, the joint axes of joints 4, 5 and 6 all intersect at a common point, and this point of intersection coincides with the origin of frames 4, 5 and 6. Furthermore, the joint axes 4, 5 and 6 are mutually orthogonal. This wrist mechanism is illustrated schematically in figure 4. In this experiment, forward kinematics of Puma 560 is described through a virtual model. The forward kinematics problem is concerned with the relationship between the individual joints of the robot manipulator and the position and orientation of the tool or end effector. Now, general terminology in robotics, workspace. It is nothing but the reachable workspace of a robot's end effector is the manifold of reachable frames. Accuracy. Accuracy refers to a robot's ability to position its wrist end at a desired target point within the work volume, and it is defined in terms of spatial resolution. It depends on the technology and the control increments. Repeatability. Repeatability is a statistical term associated with accuracy. If a robot joint moves by the same angle from a certain point a number of times, all with equal environmental conditions, the target is always missed by a large margin. If the same error is repeated, then we say that the repeatability is high and the accuracy is poor. Safety. The ability to reduce the human robot impact force and ensure human safety is a fundamental requirement for human friendly robots. Forward kinematics. Forward kinematics mainly deals with constructing a Dewitt-Hardenberg DH transformation matrix with Puma's parameters obtained from a DH parameter table shown below. Now this is figure 2 indicates kinematic parameters and frame assignments for the Puma 560 manipulator. Figure 3 kinematic parameters and frame assignments for the forearm of the Puma 560 manipulator. Figure 4 schematic of a 3R wrist in which all three axes intersect at a point and are mutually orthogonal. Now this is the table 1 Puma 560 DS, that is Dewitt-Hardenberg parameter table. This is the link, first column link 1, 2, 3, 4, 5, 6. It is noted by I. Then this is alpha I1. Different angles are there. 0, minus 90, 0, minus 90, 90, minus 90. Then AI 1 M 0, 0, A2, A3, 0, 0. DIM 0, 0, D3, D4, 0, 0. Theta I, theta 1, theta 2, theta 3, theta 4, theta 5, theta 6. Now transformation matrices for of 6 joints for Puma 560 robot. Therefore, these are the transformation matrices. Now Puma kinematics diagram. See that this is the robot. Kinematic means motion, study of motion. Therefore, this diagram indicates different joint motions of the Puma robot. Simplified drawing of first three links of Puma 560 with transformation frames approximate appropriately. See that different when this Puma robot is there, it will move. How that joint or how that different positions of the joints will be there. See that this is the waist 320 degree. It can move. Then this is the shoulder joint 250 degree. This is the elbow joint 270 degree. This is the wrist bend 200 degree. This is the flange 532 degree. Wrist rotation 300 degree joint 4. Therefore, there are 1, 2, 3, 4, 5, 6 joints are there. This is the theory. Now we will see objective. First, to identify the geometric relationship between input and output motion parameters of Puma 560 robot manipulator. Formation of the transformation matrix through which a relationship is established between different links of the manipulator. Simulate the robot motion for various inputs of joint angular value. To have a brief idea about the workspace through a 3D graph plot of manipulator position for various inputs. Then procedure. First, insert different values of theta within the joint range as prescribed in theory part, and then click OK to get the output orientation and position of the end effector. Second, to see the individual movements of the links, drag the sliders on the controller panel. The transformational matrix of a particular position and orientation can be obtained either through input panel or via the controller. Manipulator position is shown in a 3D graph for every submission of joint values. The view can be rotated about a point by keeping the left mouse button pressed and rotating the mouse. The view can be translated by keeping right mouse button pressed and translating the mouse in the desired direction. The scroll button or middle mouse button can be used for zooming. I will see the video. See the video. Puma 560. Okay, this is nothing but video of the this Puma 560. I will see simulation. Okay, now we will enter different values of theta. theta 1 to theta 6. Okay, first we will enter 25, 45, 60, 90, 40, and theta 6 we will see 30. Theta 3 should be between minus 225. We will write 40. Now you just see how this robot will move. Robot arm will move. See that it is processing here. See that how the position has been changed. Earlier position was different. Now what is the position? See that how this it is looking. Hmm? See that earlier position is different. Now this position is different. Now again I will enter different values. Theta 1 suppose 45, theta 2 65, theta 3 30, theta 4 suppose 85. This is 45 and this is suppose 35. Okay, this is nothing but two robots experiment. Now we will stop here. Thank you very much.